Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 2, Lesson 6. We are continuing Unit 2, Thermodynamics, and today we're going to talk about the heat engine, which we've already been talking about, just not by name. So this little cylinder that contains some gas can be called a heat engine. And we call it a heat engine when we use the gas to do work for us. If the gas is going to expand in such a way that this piston moving up is doing useful work, we want that to happen. That's doing something for us. Maybe turning an axle and making your car go. When this is doing work for us, it's a heat engine. So we've already thought about this setup. When the piston moving is useful work on something else, we call it a heat engine. So we're going to make a PV graph. And it turns out that for it to be a heat engine, we're going to go in a cycle. We're going to start somewhere, and then we're going to go somewhere else. So we could go, some kind of weird, random, general cycle like this. We start and end at the same place. If we go in this cycle clockwise, this is clockwise, it's a heat engine. If we were to go the other direction, it would be called something else. That's a different lesson. But for right now, if the cycle is clockwise, then it is a heat engine. So let's look at this not so much in a super general way. Let's look at something that's a little easier to analyze. What if my PV diagram is a square or a rectangle? Let's just see what's going on. And again, it's going to be a clockwise loop. Doesn't matter where we pick to start, but let's pick here. So we'll call this cycle A, B, C, D, A. A, B, C, D, A. And it has 4 parts: A to B, B to C, C to D, and D back to A. Let's talk about the work done for each of those 4 parts. A to B, B to C, C to D, and D back to A. Is it obvious that the work done in 2 of those parts is 0? Is it obvious that the work done in 2 of those parts is 0? Remember, we said that the work done on the gas, is negative P delta V. I hope that sounds familiar. So for A to B, delta V is 0. And for C to D, delta V is 0. And if delta V is 0, the work is 0. Now, these other 2 parts from B to C and D to A, the work is not 0. So let's take a look. From B to C, I want the area under the curve. So this area is the absolute value of that work. The absolute value of that area is the amount of work. And because we're going from B to C, because the volume is decreasing, the work done on the gas is positive. As we go from D to A, this is the area under the curve. And I think you can see that this green area is bigger than the purple area. And that work is negative. Because remember, work W is defined as the work done on the gas. So when the gas is compressed, we're pushing on the gas in the same direction as the piston is moving. That's positive work. But when the gas expands, we're pushing on the gas opposite the direction that the piston moves. And so then negative work is done on the gas. And so that's why this is negative. Do you see, let's look at a couple things. First of all, do you see that the negative area is bigger than the positive area? The negative green area is big. The positive purple area is small. And therefore, the sum of all of these, the sum is negative. So that's one thing to notice. So if W, work, is defined as the work done on the gas, and that sum is negative, then what that means is, in essence, there is not work done on the gas, there is work done by the gas. And then the other thing I want you to notice is that this green negative work added together with this purple positive work gives me a net total work of this black area. The black area equals the net work done by the gas. It's going to be a negative number because work is defined as the work done on the gas, but that's how much work is done by the gas. And that can be expanded through the properties of calculus, which we will not use. But in general, anytime there is a loop, a cycle, where we start and end at the same place, it is the area enclosed that is the work for the process. And if it's a clockwise loop, then there is net work done on the environment by the gas. So it's an engine, it has done work for us. So that's the big idea of a heat engine. And the area there is the net work done by the gas on the environment, the work done for us. So there you go. And again, I said that's an engine. When we're going clockwise, when we're going counterclockwise, it's that other thing called a heat pump that we're not talking about today. So clockwise process. All right. Now let's just talk a little bit about the fact that this is in fact a cycle. We start here and we end here. We start and end at the same place. U, the total energy of the gas, is called a state function. So if U is a state function, it means that the total energy of the gas at A is the total energy of the gas at A, regardless of how we got there. So if I start at A and I go in this kind of circle-y process, or if I go in the nice defined square process, or if I go, in a super weird kind of process, it doesn't matter if I start at A and I end at A, because U is a state function. If I start and end at A, delta U for a cycle, that means a cycle, it's a little loop with an arrow, equals 0. The change in internal energy, if I start and end at the same place, is 0. The change in internal energy, if I start and end with the same internal energy, is 0. So how does that relate to our first law of thermodynamics? Delta U equals Q plus W. Well, if delta U equals 0, that means Q plus W equals 0, which means Q and W are opposites. Since W for this clockwise process is going to be a negative number, it's the work done by the engine on the surroundings, then Q must be the same size, the same number of joules, but the opposite sign. W is a negative number of joules, so Q for this process would be a positive number of joules. Q is the heat added into the engine, and it's positive. So what's happening in this cycle is heat is added and work is done. And the heat added and the work done are the same as each other. That sounds kind of magical. I put 35 joules of heat energy in, and it does 35 joules of work for me. It's actually not quite that good, and we'll talk about why in a minute. But that's what Q means, and that's what W means. So I have a picture to show you from the textbook, or show your textbook. I'm going to grab the textbook because it's not right there, but I'm going to turn to figure 12.9 on page 400. Did you miss me? So I'm on page 400 in my book, and I'm looking at figure 12.9. So it's this picture here. And it's a schematic diagram. It's not an actual photograph. But so this is my heat engine, which remember is just gas. And it shows W sub ENG. Let's zoom in on that a little bit. WENG. So this is the work done by the engine on the surroundings, or the work done by the gas. This W is W in this equation, delta U equals Q plus W. What's tricky is that there's actually two values of Q, two amounts of heat. There's this heat, which we call Q sub H, and this heat, which we call Q sub C. What happens is there is some heat added to the gas, and then work is done. And if that were all there is in the picture, that would just be super, super, super cool. We add 35 joules of heat energy and we get 35 joules of energy out. Yay, that would be great. Unfortunately, when we add heat to the gas, and as the gas, expands and contracts, some of that heat energy slips out into the environment and heats the environment. And so this is the heat lost to the environment. This is the heat added. If I'm burning a candle, or if I have a Bunsen burner, that's my energy that I'm putting in that I would like to turn into useful work. But whenever I put energy into something, some of that energy just leaks out. And so this is loss. And so neither of these two Qs, neither QH nor QC, is Q in this equation. I have to take both of these into account to get Q for the equation. We'll talk about that in just a moment. But the idea is, if I'm talking about my car, which is an old-fashioned gas kind, not one of these fancy new electric ones. But in the car, we are the engine gets really hot. So if you touch the hood of the car after it's driven for a while, that's all because energy is just being wasted and released into the environment. So this is wasted, lost energy. Oh, that's too bad. So this number, and we'll think of these both as positive numbers. That's why these absolute values are here. So the number of joules that we add here minus the number of joules that come out is the net heat added. And that's going to be Q in this equation. So to find Q, the heat added, it's the heat added minus the heat lost. And these would be positive numbers in this equation. So in other words, if I have my little Bunsen burner underneath and I add 100 joules of energy, but 40 joules of energy gets lost to the environment, then Q in this equation is only 60. If I add 100 and I lose 40, then I only have 60 joules, which means I can only do 60 joules of work on the environment, not that whole 100. I expended 100 burning stuff, but 40 of it got lost, so I only got 60 out. So this is called Q hot. QH stands for Q hot. And we're assuming that we've got some hot reservoir, so something hot outside that's transferring heat in, it's transferring energy in. And then the surroundings might be considered cold at another time, and then heat is being lost. So anyway, that's what all these three things mean. Let's take a peek at these equations. Oh, I keep pointing to my other piece of paper here to talk about this equation. When look at it, it's right here. Delta U is 0. I told you that. So Q plus W add up to 0. So Q and W are opposites. Very good. And then W is a negative number, so negative number is a positive number. That's the work done by the engine. And so the last equation shows that W sub ENG, the work done by the engine, the work done by a heat engine equals the net energy absorbed. The net energy, we do absorb, but we also release. So the net of that. And so what they did is they thought of Q hot and Q cold, both Q hot and Q cold, not old, Q hot and Q cold, both think of them as positive numbers. And this one minus this one is that net. It's exactly what I just said. Very good. So it is the fact that we lose heat to the surroundings, that some of the heat that we wanted to turn into work just went into heating up everything else around. That makes things not perfectly efficient. I want to burn 100 joules with my Bunsen burner and get out 100 joules of work. I'm not. I'm going to get less work out. Okay. And so then there is this concept of efficiency. And so with the super easy numbers I just talked about, if I add 100 joules of heat energy in, but 40 of it heats the environment, then only 60 of it does work for me. So I would say that's 60% efficient, because I got 60 joules of work, but I put in 100 joules of heat energy. 60 divided by 100. Let's see how that relates to these efficiency equations. Lowercase cursive or lowercase italic e means efficiency, and it's the work done by the engine divided by the heat I put in. So it's this number divided by this number. And then, of course, the work done is this number minus this number. Zoom out so I don't have to keep moving my book. So this Q hot stays Q hot. The work done by the engine got replaced by Q hot minus Q cold. And then when I have two things, when I have a difference over a common denominator, I can make that Q hot over Q hot minus Q cold over Q hot. But Q hot over Q hot is 1. So any of these equations would work for efficiency. The work done divided by the heat in, the difference in these two heats divided by the heat in, or 1 minus the ratio Q cold over Q hot. Any of those would work for finding the efficiency. Oh, here's my same picture here. The area enclosed is the work done by the engine. So that is the introduction to what a heat engine is. And we're going to talk about different kinds of processes. Here's a process, it's clockwise, it must be an engine, where we have an isobaric, an isochoric, and then a curved part, which if we don't read, we don't know what it is, but if we read, they'll probably tell us something about it. It's right in there. Anyway, and then there's all kinds of other fun processes we could look at. I'm looking for examples. Here's one we're going to talk about in a couple days. Ooh, there's 4 parts. That's a really fun process. We'll talk about it in a couple days. Anyway, lots of talk about that. But since when I have a hot thing, when I have this gas, there is always an environment. So there's always going to be some heat that leaks out, which is called heat lost to the environment. Because that heat is never zero, I cannot have 100% efficiency. The efficiency must be less than 100%. Well, sometimes that is called the second law of thermodynamics. Some of the energy, the heat energy that I put into the engine, has to be lost as heat to the surroundings. I cannot convert all of that heat into useful work. So that's called the second law of thermodynamics. And there's lots of ways of saying it. But basically, where some of our energy gets lost to heat in the surroundings. And that heat in the surroundings is much harder to harness and gather and use. And so sometimes that loss of energy, we don't lose the energy, it just gets transferred to a less useful phase. That is called an increase in entropy or an increase in disorder. So one way of saying the second law of thermodynamics is that this entropy or disorder is always increasing. But in this context, the second law of thermodynamics is we cannot have 100% efficiency. Our efficiency must be somewhat less than that. Since I did mention the word entropy, which is disorder, I'll just say that it is a physical quantity that we measure, and it has the unit joules per Kelvin. No, I'm not just kidding. No. So that's a good thing to add to your quantity and unit chart. The entropy is measured in joules per Kelvin. Okay, that's all I have for today. There is another video coming up about a specific kind of heat engine. I showed you a quick picture of it. But so the next video, we're going to talk about the Carnot cycle. Anyway, for now, I hope you have a great day. And whatever you do, don't break the laws of physics.